Hello and welcome to the sixth lesson in Unit 4. And today we're talking about laminar and turbulent flow. So, today I want you to be able to define and describe with some examples the difference or the concept between laminar and turbulent flow inside of fluids. So here we go. There's a couple definitions which you have already in front of you. So I'll talk about each one by one. So fluid dynamics, that's what we're talking about today because we're talking about the flow of fluids. So we're talking about fluid dynamics, and that's the study of the factors that affect fluids in motion. Viscosity, and you've heard this probably if you've watched commercials with promoting oil products. Talk about viscosity breakdown. Viscosity, it's a property of a fluid that determines its resistance to flow. A high viscosity, all right, a high viscosity means a high resistance to flow. So an example of high would be cold maple syrup. All right, when you go to get that maple syrup that's coming out of the fridge, out of the bottle, all right, and that's, I'm talking about the sort of the corn syrup, it is a high viscosity, doesn't really want to flow out. Where if we have a low viscosity, for example, I would say water would fall in that category. It is generally wanting to flow. So high viscosity means that it doesn't flow very fast. Laminar flow. Laminar flow is fluid flow in which adjacent regions of fluid flow smoothly over one another, and we're going to talk about that in more detail. So if it's not clear, which I understand completely at this point, we're going to talk about it in much more detail, so I'm not going to give you too many examples at this point. Turbulent flow, that's fluid flow in which a disturbance resists the fluid's motion. Okay, so those two we're going to talk about in much more detail today. So at the bottom of the first slide here, talking about fluid flow inside and around objects. So in this first one, I'm going to go for example, this is in a pipe. Okay, this could be a river. So those are the shores of the river. It could be a trough, an eaves trough, for example. So inside a pipe, a river, a trough, what happens is that on the edges, water is experiencing a frictional force. So on the outside, the water, and those are velocity vectors. All right, so I'll just put velocity vectors. So it's experiencing some friction. The farther you get away from the wall, the higher your velocity because you're not in near as much contact with that wall. So anyone that's paddled and been in a canoe before on a river, you'll know that the fastest moving water is in the center of the river, and that's why. Same thing inside a pipe. For plumbers and so on and so forth, your highest fluid flow is through the center of that pipe. Okay? So again, on the edges have friction, so they're opposing the motion of that water. All right? Now, if you are moving around a pointed object, so we have our velocity vector on the outside, not being affected by that object, and then your velocity for the fluid as it tries to go around gets split off here. We get that dividing force, and what happens is that there's a little bit of a buildup, is what we call. I'm going to talk about that in a little bit more detail. So there's a buildup because all the water is being pushed to that side. Okay, so that's if you have some kind of blockage inside a fluid flow. Moving to the next slide. I'm going to talk about turbulent flow. So the two examples I have here, what I'm going to do is, this one's going to be what we'll call low velocity, which I probably drew that vector a little long for a low velocity. And this one we're going to talk about a high velocity. And you can think about this, if you're driving your car and your hand's out the window and it's kind of behind the mirror. This is kind of what we're looking at here. So what happens at a low velocity? Well, we have all these parallel flow lines coming in. And what happens as it reaches that object, the lines that are closest that have to go around create an eddy swirl, we call them. All right. So those in there that I just sketched there are what we call eddies. And those eddies cause turbulence. So turbulence is that, that fluttering force that's, if you put your hand there, it wants to push your hand or sort of run it all over the place. So at a low velocity, that's what it looks like. However, if I draw the same number of lines here, so 1, 2, 3, 4, 5, 6. Now at the high velocity, those eddies are much more intense. So I'm going to draw them a little, or exaggerate them. All right, so those eddies, because it's a higher speed, more eddies are created and the intensity of the eddies are magnified, and what they experience is a higher or more intense eddies. And that is what aerodynamics engineers and designers try to avoid, because that turbulence causes friction, it causes vibration. When you're driving and you hear your part of your car vibrating, it's from that turbulent flow around it. It's causing that vibration, and that's what they try to avoid when they're doing automotive design. So as we move down through the note here, some of the common problems associated with turbulent flow. And when you lose, what's happening with that turbulent flow is you're losing kinetic energy. So obviously with sewage pipes are a huge concern for local municipalities. I'm not going to go into a whole lot of detail here. I'll leave some to your imagination. But you got a sticky product moving through your sewage pipes, which causes buildup, and so on and so forth, which is an increase in friction, increases friction on the walls. So a lot of those sewage pipes that are going in the ground, the interior surfaces are coated. So both the plastic and the concrete pipes get coated with kind of a plastic polymer, okay, or treated in the factory. And also what they can do, they can dump liquid plastic into the system. So they can, I'll put dump liquid plastic into the system. So this liquid plastic, kind of like if you think of it as a graphite, if you ever touched graphite, it reduces friction. So dump liquid plastic in the system. What it does is it makes things less liable to stick to walls and flows through the system a little bit quicker. Okay, fire hoses. Obviously, when we're fighting fires, you want the maximum range of that hose. So it's the same thing there. You can reduce that, reduce the friction by injecting a lubricant product. So fire hoses obviously don't become clogged, but the material they use in order to store vast amounts of hose, it's got to be something foldable, and they use that kind of canvas material. So inside that material, there's friction, same as the sewer pipes, different reason though. So again, if you inject or coat the inner walls with liquid plastic or some similar product, there's many out there, what happens is you reduce the friction, which increases or allows for fires to be fought at a larger distance because that friction is reduced. So those plastic particles that I've been talking to, they make the walls slippery. So the sewer pipe walls, the fire hose walls, they reduce the stickiness. So it's kind of neat because medical science has also kind of jumped onto this, and there is products that they inject to reduce the buildup inside of human arteries, which leads to heart attacks because of clogged arteries. So also a biological product as well. So it extends into the medical sciences, the turbulent flow. So one of the major fields that you can get into is aerodynamics, and there's many different. It's not associated necessarily with the design of airplanes. I got a couple more terminology definitions we got to talk about. So drag, people have probably heard this before. Drag is the force that acts against the object moving through a fluid. Streamlining is the process of reducing the turbulence. That was what we were talking about before. We want to reduce that turbulence. So if we streamline it, it allows the fluid to move around more quickly. And then drag coefficient, and it's a quantity that is used to determine or numerically assign a value to the resistance of an object in water. And if you look off to the right here, I have a chart that has some general shapes and the drag coefficient, and that's that 0.47, 0.42 is give it as a percentage. So a sphere has 47% drag coefficient, a half sphere is 42, a cone's 50. So it kind of gives you, relative to each other. So the example I have here is the cyclist. So if we look at our cyclists, the different forms, so we have upright, we have drafting, that's following behind. So if you get behind a large transport truck or a larger vehicle, you're drafting. The next position we have is what we call the egg shape. So I'm just going to make a little bit more space here. So here we have egg shape is what they call this. And finally that laid back position, we called it kind of the crouched egg, or I believe they call this fairing, and it's just that laid back position. So I just wanted to give you an idea, and this is true, you can look at vehicles this way as well. So if we look at the variety of shapes here, what happens when we're talking about that upright position, if you compare it to the shapes on the right side here, we have a pretty flat surface here. So we're looking at coefficient of drag. So when you're cycling upright, your drag coefficient's about 1.1. Whereas if you're in that drafting, you're following behind someone, you reduce your drag to about 0.5. So if you think of a vehicle, how much it has to work, you're reducing the workload by half if you're following in tight behind someone. If you're in that crouched or egg position, all right, you can reduce your draft, and this is why when you watch Tour de France and all the long bike races, they get down as low as they can. You're reducing that drag on you. And then that bottom position, actually, even though it looks quite uncomfortable and not a whole lot of fun, you reduce your draft down to about 0.1 in that position. So it's a significant decrease in drag. So it is a lot easier going through the air in that position, but again, to me it doesn't look a whole lot more comfortable, but I'm not an avid biker. So generally what happens when they do that aerodynamics, they simplify the object to basic geometric shapes. So this is old school because now with technology, with computers and stuff, they can model turbulent airflow, but they go back to the basic objects, and then they can look at this chart on your right here, and they can match up the proper geometric shape and approximate the drag. But now we computer model. Once they do the modeling and they do the design, they put it in a wind tunnel to analyze turbulence. So what I would do now is I definitely would go to the website, the demos, because it shows, I think, Ford and Dodge, how they look at aerodynamics in their design. So anyway, if you have any questions, let me know, and we'll get them cleared up the next day. Good luck.